All right, so the second murky point from chapter 2 that I want to cover is ocean currents. In particular, what drives ocean currents, and then in the context of ecology, how do ocean currents affect biological interactions? So for the first piece, I'm going to try and simplify ocean currents as much as I can. They're very complex. You could probably um, take several courses on ocean currents and barely touch the surface, so to speak, in terms of the physics and chemistry that's involved. I'm going to do my best also to sort of present them in a way that matters to ecology. So what about ocean currents do we need to understand in order to understand how ecosystems function? So we know that ocean waters are constantly on the move, and how ocean waters move influences, at a big scale, it influences climate, as well as living conditions for plants and animals, even on land. Now, how we characterize ocean waters, or that movement of ocean waters, is simply currents. So currents are just patterns of water flow over time and space. Now, current flow in the ocean is very complex, and it's affected by many things. First of all, it's affected by wind. So winds drive currents that are on or at the ocean surface, right? So if you think of the vertical dimension of the ocean, wind is affecting the water that's on top. This wind has an impact in the open ocean. It also has an impact on, slightly differently, if we're looking at coastal areas. The second thing that we have to consider is thermohaline circulation. So this is sort of a complicated word, but if we break it down, thermohaline simply means salinity and temperature. So the chemical composition of ocean water, as well as its temperature, is going to affect how it circulates. So again, if we think about the vertical dimension of the ocean, currents are going to be affected by thermohaline circulation or conditions, whether they're at the top or at the or whether they're very, very deep, and they interact, and I will explain that in a little bit. And then the third thing is the bottom topography. I didn't want to leave that out, but I did want to mention that bottom topography, or that landscape of the ocean, of that ocean, especially in the open ocean, is going to affect how currents flow. But we're not going to talk about that. And then the last thing is the Earth's rotation, or the Coriolis effect, which I didn't ask you to really focus on in your content outline, but I'm just going to explain it a little bit so you understand how it impacts current flow. So this is a very simplified list of what impacts currents. So first of all, the Coriolis effect. If you think about the rotation of the Earth on its axis, the atmosphere is going to be deflected toward the right in the northern hemisphere, so where we are. And if you're in the southern hemisphere, it's going to be deflected towards the left, which results in curved paths. So these curved paths influence how air flows, so wind flows, and it also influences how water flows. So this deflection, or this Coriolis effect, is going to, like I said, it influences wind, and it influences surface currents. Now, wind is what typically drives surface currents. So for that reason, if we look at a map of prevailing winds, and prevailing winds are directly impacted by the Coriolis effect, and it follows a pattern that's dictated by that, these winds are also driving these surface currents, which results in a very similar pattern if you're looking at prevailing winds or surface currents. Not exactly the same, but very similar. So now, if we consider the chemical aspects of the surface water, we know that water that's near the surface tends to be warmer, and it's less salty, and therefore it's going to be less dense than that deep, chilly ocean water that's beneath it. So in general, when we think of this warm tropical surface currents, as they pull water from the equator towards the poles, that water is going to cool down, and it's going to become denser. And some of that water is actually going to form ice. And when that water forms ice, it leaves that salt behind, so it makes everything else even saltier and denser. So the super dense, cold water in the poles is going to do what we call a downwell, or it's going to trigger a downwelling process where it's basically going to sink. And then as it sinks, it moves towards the equator. And then as these deep ocean currents are pulled toward the equator, it's going to hit coastal zones where it's going to warm up and it's going to rise to the surface because warm water typically is less dense, right? And it's going to rise. So this is a process that we call upwelling. So again, the rise of this deep, cool water near the coast, upwelling as we call it, is also going to be impacted by localized winds that are blowing across the ocean surface and push water away from an area. So often it occurs in a pattern that's parallel with the coastline. But it's going to allow that water, when that wind carries that water away, that surface water away, it's going to allow that deeper water to upwell, bringing that actually cooler water up toward the surface. And as it brings that cooler water, it's also going to bring some other things with it. So that subsurface water that rises to the surface as a result of this upwelling is going to be colder. It's going to be very rich in nutrients, and it's going to be very biologically productive because it's going to pull all of that decaying organic matter that's sitting on the floor of the ocean. It's going to pull that back up and make it available. So it's going to pull it up to those photic zones or those light zones near the surface, and it's going to become available for essentially the start of the food chain, which is very important and something that we'll look at a little bit in better detail in terms of aquatic ecosystems in the next few chapters. So essentially, what I'd like you to get out of this is to understand that those coastal regions are extremely biologically productive because of these nutrients that are brought here through upwelling. And this is where we find our richest fishing grounds. So most of our marine fisheries, our most productive marine fisheries, are found in these areas that have the most action in terms of upwelling. For example, in particular, the western coast of Africa and South America have a year-round upwelling pattern that supports extremely productive fisheries. Again, so this image in red, this highlights the major upwelling areas along the world's coast. And again, upwelling just simply occurs when winds blowing across the ocean push that surface water away from an area, and that subsurface water rises from beneath to replace the diverging surface water. So again, these subsurface waters are colder, they're biologically very rich, they contain lots of nutrients, and so therefore this is where we tend to have extremely productive marine fisheries. All right, so we also have to consider thermohaline circulation, which again is just the saltiness and the temperature of ocean water. Just think of it as salt and temperature. So the thermohaline circulation drives a global scale system of currents, which is referred to as the Great Ocean Conveyor Belt. It's also called the Global Conveyor Belt, but you get the idea. So the conveyor belt begins on the surface of the ocean, so that, if you're thinking vertically, that very top layer of water in the ocean near the pole in the North Atlantic. So the water here is going to become very chilled by those very, very cold Arctic temperatures. As it gets colder, it gets saltier because when sea ice forms, again, that salt does not freeze and is left behind in the surrounding water. So that cold water is now more dense due to the added salts, and it's going to sink toward the bottom of the ocean. Surface water here moves in to replace that sinking water, thus creating a current. So now as this really deep water moves south between continents, past the equator, and down toward the ends of South America, towards Africa, the water is going to cool, especially as it hits this very cold polar air temperatures down here. The water is going to cool and it's going to sink again, as it did in the North Atlantic, and that conveyor belt then is going to get recharged. Now, as it moves around Antarctica, two sections are going to split off the conveyor and turn northward. Now, one section is going to move toward the Indian Ocean, and one section is going to move towards the Pacific Ocean. These two sections that split off, they're going to warm up, and they're going to become less dense as they travel northward toward the equator. And so that they rise to the surface, again, if you remember what this is called, upwelling, right? So anytime water rises to the surface, it's upwelling. And then they're going to loop back southward. They're going to loop back southward and westward toward the South Atlantic and eventually return to the North Atlantic, where that conveyor belt or that cycle is going to start again. Now, this conveyor belt is very, very, very slow. So it literally moves like a few centimeters per second. Then those wind-driven, or we didn't talk about tides, but there's also tidal-driven currents that are in coastal regions. Those tend to move very fast. These deep conveyor belts are moving very, very slow. All right, so it's very important to remember. And what I also want you to understand is that this conveyor belt is very important in terms of transporting ocean nutrients and carbon dioxide. So it triggers or regulates these cycles of ocean nutrients and carbon dioxide. So warmer surface waters tend to be depleted of nutrients and carbon dioxide, but when they travel through this conveyor belt as deep or bottom layers, they're gonna pick up some nutrients and carbon dioxide, which is very important for driving productivity in an ecosystem. So the base of the world's food chain depends on these very cool nutrient-rich waters that support the growth of algae and seaweed subsequently. And we'll get into more detail about that when we talk about aquatic ecosystems later on. And again, something I want to touch on and just remind you of that these ocean currents, when they move through these tropical waters, they're picking up heat, right? So we know that these middle latitudes, this is where we're getting most of the solar radiation. 40% of the heat exchange between the tropics and the poles is due to these ocean currents, and the rest of it, that remaining 60%, is due to being transferred by winds. But it's very, very important. So in particular, when you're looking at this pattern, I don't expect you to memorize this circulation pattern, but just understand that if you were looking at this, understand why here. Why is this water moving this way? It's warm and it's shallow, right? These cold and salty, very deep currents are moving this way. And when they get here, they're going to pick up heat when they pass through the tropics, right? And so they're going to rise to the surface, become less dense, which is going to drive the cycle further. So I hope you understand this a little bit better. As always, please let me know if you have questions at all.